This video is made by Ajit Kumar Nair, rehabilitation professional, counseling psychologist, and clinical hypnotherapist from Nair's Epigenetic Wellness, Indore. Humans navigate the physical world using a hidden internal GPS, the vestibular system. This system operates silently beneath our familiar senses, mapping our position in space at every moment. For an autistic child, daily activities like running across a field or riding a bike require immense conscious effort. The complexity of coordination is magnified when the brain receives inconsistent signals from its internal balance sensors. Specific physical patterns like constant spinning, rocking, or climbing frequently emerge as a result. These actions serve a vital purpose, acting as active attempts to stimulate the vestibular system and achieve a sense of spatial grounding. Conversely, many individuals experience a profound fear of movement or avoid playground equipment entirely. Without the mechanical precision of a reliable balance system, even simple changes in elevation feel unpredictable and threatening. To find the root of these behaviors, we must look past the external symptoms and examine the biological hardware of the inner ear. The vestibular system resides within the temporal bone of the inner ear. It utilizes 3 semicircular canals to detect rotation and specialized sensors called the utricle and saccule to monitor head position relative to gravity. This symbol reflects a continuous feedback loop. The inner ear detects motion, sends data to the brain, and the brain immediately recycles that information to refine our posture and movement. The cerebellum acts as the main processing hub for this data. It integrates raw balance signals with visual input, ensuring our physical actions remain smooth and controlled. Neuroimaging reveals that many autistic individuals have altered gray matter volume in the cerebellum. Coupled with atypical connectivity, these structural differences disrupt the flow of balance signals, causing the feedback loop to stutter. When this loop fails to close, the brain cannot accurately determine its position in 3-dimensional space, leading to a state of constant spatial confusion. This internal confusion places a heavy tax on the body. Simply sitting upright or standing still requires constant, exhausting effort, as the muscles must overcompensate for the lack of intuitive postural control. We can visualize this energy drain using the model of an electric battery. For an autistic individual, maintaining basic posture is a high-demand activity that depletes internal reserves, causing early fatigue and reduced endurance in daily tasks. Physical instability often triggers a physiological stress response. The persistent fear of falling or losing spatial control keeps the brain in a state of high alert, fueling an anxiety amplification cycle. This cycle makes surrounding environments feel overwhelming. As anxiety rises, the vestibular system becomes even more sensitive to motion, making crowded or brightly lit spaces feel like they are spinning out of control. This combination of exhaustion and anxiety frequently leads to social withdrawal. Avoiding movement-intensive environments becomes a necessary strategy for maintaining emotional and physical safety. Because every individual is unique, clinicians sort these challenges into specific profiles. We categorize sensitivities into hypersensitivity, hyposensitivity, or reflex differences to ensure that support strategies match the specific neurological need. Specialists use tools like computerized dynamic posturography to measure these differences objectively. These assessments provide a clear map of how an individual's balance system is functioning in real time. Rehabilitation focuses on rebuilding the balance loop. Rhythmic activities like aquatic therapy, martial arts, and yoga help individuals develop coordinated, purposeful movement in a safe, controlled context. Schools can also adapt the environment to support these needs. Strategies include clearing physical pathways, providing wobble seats for postural support, and integrating scheduled movement breaks to prevent sensory overload. These modifications act as a secondary power source. By reducing the physical effort needed for stability, we free up the student's energy for academic learning and social engagement. A child's unique movement pattern provides a direct window into how their brain processes its surroundings. By supporting the underlying vestibular architecture, we build a foundation where physical confidence and social